To start with, can I see a show of hands? How many of you have seen this and been frustrated and then been stuck to a wall waiting for your batteries to charge up? And then eventually the batteries die and you have to throw them away or replace them. How inconvenient, how wasteful. Now, electronic devices are shrinking in size, and this is why you can fit a computer in your pocket. The power requirements are shrinking as well. And so the question that we're trying to answer in my lab at the University of Cambridge is, can we design a power plant that also fits in your pocket, that can produce power on the go, that's convenient and accessible? And it's a very relevant question because there are many devices these days, for example, wireless sensors, which connect everyday objects, which report on vital physical parameters. And these can be used for early fault detection systems, for healthcare monitoring, for smart and efficient lighting. And so how do we power these? A lot of these sensors are going to be implantable, or they'll be embedded, and they'll most definitely be small. You'd want to have as many of these in the environment to make an efficient network in order for these to work properly. So wouldn't it be great if these devices could run by themselves? Wouldn't it be great if they could be somehow self-powered? But we know that energy cannot be created, or for that matter destroyed, but it can be converted from one form to another. And so the question is, can these sensors run by themselves using the energy that's available in their natural environment? And so what kind of energy would this be? For example, it could be the sun, but this is not always convenient or accessible. It could be waste heat, but then you would need massive temperature changes for this to work efficiently as of now. And if you stop to think about it, you'd actually realize that you can't stop, that is. Our bodies are a constant source of mechanical energy, be it through walking or breathing or the blood flowing. There are plenty of sources of vibration in nature that we can tap into. And so this enormous amount of mechanical energy that's available to us, if we could use this to power the sensors that work in them, that would be great. And how can we do this? It turns out certain materials, by virtue of their crystal structure, are piezoelectric, which means they can interconvert mechanical and electrical energy. Essentially, if you squeeze them, you can produce electricity. This is what you have in gas lighters and in microphones. And piezoelectric materials have been known for more than a century, and vibrations have been around forever. So the question is, why now? Why is this interesting now? Well, it turns out that we're at a unique stage in the evolution of modern electronics where the power consumption of devices has reduced to such an extent that it is now feasible to power them from ambient vibrations. And in order to do this, piezoelectric nanogenerators can convert vibrations that are typically small into useful electrical energy. Now, the research in nanogenerators has traditionally been in piezoelectric materials which are ceramic in nature, and hence they're brittle and prone to mechanical failure, which is no good. We are more interested in piezoelectric polymers, which are poorer counterparts in terms of their piezoelectric performance when compared to ceramics, but they're flexible, they're robust. And so we have a few tricks up our sleeves. First, we work with nanomaterials, and this is because on these length scales, the piezoelectric properties can be significantly enhanced. Also, being nano means that they would most likely satisfy our requirement for fitting into your pockets. However, the trouble with anything nano is finding a reproducible way of making lots of it. And so we are interested in scalable nanofabrication techniques, and we demonstrated one of these when we made a nanogenerator based on piezoelectric polymer nanowires, which when tapped could produce enough energy to light up an LED, which is great. But we want to do better. As material scientists, we are constantly looking for ways by which we can design materials to suit specific needs. And so we want a material that has superior energy harvesting performance, but which will not break up in the process. And so to do this, we combine ceramics and polymers to make these hybrid nanocomposite materials, which basically combines the best of both worlds. And looking further, we need to keep an eye out for the environment, because a lot of the best piezoelectric materials contain lead or other heavy metals, and which we're keen to avoid. And so we turn to nature to look for biological forms of piezoelectric materials, such as bone or cellulose, and coming up with ways by which these can be integrated into these nanogenerators. We also look at other ways by which we can enhance the performance of these materials by making them more sponge-like, so that you can get more strain, you can squish them more easily. And we do this by making these mesoporous structures in these piezoelectric materials. So in conclusion, I hope I've been able to show you how we hope to achieve our goal of self-powered, fit and forget devices. And I hope you've been able to see how this affects the bigger energy problem. Piezoelectric nanogenerators can revolutionize the wearable technology industry, healthcare monitoring, smart infrastructure. At the very least, I hope they inspire us all to lead more active lifestyles so that we can keep our beloved gadgets up and running. Thank you very much.